Welcome. I'm Conrad Metcalf. I am the director of the New York Building Performance Contractors Association. For those of you unfamiliar with BPCA, we are a 20-year-old nonprofit trade association that is working to build a viable market for energy efficiency services, the specific services around energy efficiency. I want to welcome you to this third webinar in our second series to promote the practical deployment of air source heat pumps across the state. The goal of this particular webinar is to highlight the errors that tend to undermine consumer confidence and to help you avoid those errors. This effort started last year with a series of inspections, Tatum Engineering inspecting air source heat pump installations, and we developed this training in response to help installers avoid the most common installation problems that tend to result in callbacks. We also hope this effort will help to attract new HVAC workers to install more air source heat pumps, because there's a lot of work to be done if we're going to be meeting the governor's stated energy goals for 2030. And before we get started, I just want to thank our sponsor for this webinar, HeatSmart Tompkins. Brian Eden heads up HeatSmart Tompkins, and he's here with us today as part of a very dedicated effort to help facilitate the transition from fossil fuels to electric heat pumps. But like I said earlier, we do need to move right along. We have a lot to cover today. We will be taking your questions as you submit them through the QA function. Submit them at any time, but we'll answer them towards the end of the webinar. And as always, there will be many opportunities to share your thoughts in the chat window. I encourage you to do that. I would also like to implore that you complete the pre-webinar survey and also the post-webinar survey afterwards. This is a very quick and easy way to support the folks that have brought you this webinar series, and it's very important. So please make time to do that. It doesn't take very much time. And now I'd like to introduce our esteemed instructor, John Harrod. John is the founder and co-owner of Snug Planet. Snug Planet is a full-service building performance contractor based here in Ithaca, New York, and a BPCA member. John, in light of the challenge you face getting through all the technical parts of this training, I'm going to hand it off to you without further ado.
Thanks, Conrad, and thank you for everyone who's attending today. Our topic here is air source heat pumps without callbacks, with the goal being happy customers and more profits for us. Our learning objectives today, we're going to go through all the steps involved in designing and installing air source heat pumps. And in doing so, we're going to identify some of the places where errors commonly occur. We're going to talk about the evolving best practices for design, installation, and maintenance. We're going to identify and look at solutions to some common installation issues. And I also want to introduce you to some of the fantastic free resources that are available through the Northeast Energy Efficiency Partnerships and their cold climate air source heat pump program. We are very excited about cold climate air source heat pumps for so many reasons. They're incredibly flexible in their application. They're efficient both for heating and cooling. They are a really cost-effective replacement for fossil fuels and for electric resistance. They're relatively simple to install, and because of all these things, they represent a really scalable path towards a low-carbon housing stock. But as we've come to find out over the last couple years, these systems can be really unforgiving when it comes to poor design and poor workmanship. If these aren't done right, you end up with poor temperature control, excessive noise, inefficient operation where they don't reach their potential to be highly efficient and instead end up driving up people's energy bills. You can get in a cycle of callbacks where you're unable to resolve the problems that were created earlier on in the design and installation process. And if they're not installed and maintained properly, they can also have a short and disappointing lifespan. So we're really going to be talking today about what we can do to ensure that we get good results and what steps we need to avoid, things that we shouldn't do, so that we can be sure that we're giving our customers excellent results every time. One of the things I really want to emphasize is that most of the problems that occur with cold climate heat pumps are due to contractor error. The equipment is manufactured under very tight quality control, and most of the problems that occur are because of applications. The wrong equipment was specified for the application. It wasn't installed properly. Inadequate quality control was done in the installation process. And we didn't take the time to instruct the end user in how to properly operate and maintain these systems. These are all totally avoidable errors that we can, and really we need to, if we want to scale these products, we need to figure out how to avoid making mistakes. A lot of the topics I'm going to be talking about today are described in a lot more detail in the NEEP resources, their guide to sizing and selecting air source heat pumps. And also in an article I wrote for Building Performance Journal called Cold Climate Heat Pumps Do's and Don'ts, which I will be sending out as part of the along with the slide deck for this webinar. But there's also a lot of overlap. Almost everything that I'm going to talk about today is described in manufacturers' trainings as well. I'm most familiar with Mitsubishi and LG products, but all the major manufacturers offer excellent technical trainings, and you'll see a lot of these points reinforced over and over again in their trainings as well. So starting with application, how do we design and select products so that we get good results? And what I've tried to do is outline a very general process and take you through it step by step. It really starts with sitting down and talking to the end user and figuring out what their goals are with this project. Then assessing the building, figuring out, okay, these are their goals. This is the building that we have to make this work in, and we need to assess the building envelope so that we know how much heating and cooling we need to keep the place comfortable. We need to evaluate the electrical service so that we know that we have enough capacity to go to a all-electric heating system. And if we're going to use existing ductwork, we need to evaluate that too and make sure that we have enough capacity. So we assess the existing building, and then we look at options. And we want to look at different ways that we can zone the systems, where to locate the ductless heads or the ducted air handlers, and how we want to control those. We have to figure out the best system and sizing for that system to match these requirements. Figure out where the individual indoor and outdoor components are going to go. And then we need to step back and make sure that all the equipment that we've specified is going to play well together. And so you're going to hear the word confirm quite a bit in this talk. One of the things that we found is that, the easiest time to fix problems is before equipment's been purchased. And as you go further and further down the line, from design to purchasing to delivery to installation, the cost of making changes go up and up. So we want to confirm early in the process, and just like a carpenter wants to measure twice and cut once, we want to check all our designs and details before we actually start putting stuff in the ground. So really a successful installation starts by sitting down with the end user and figuring out what their goals are. Are they looking for a full load solution that meets the entire heating and cooling requirements of the house? Or are they just looking for a partial load solution, something that might be used to heat and cool a bonus room or an addition, something that carries them through the shoulder seasons, and then they switch over to a different heating system in the dead of winter. So what's their goal there? Are they looking to eliminate fossil fuels entirely? It's important to talk to them about what are their comfort parameters. Some people really want every room in the house to be a very even 72 degrees. Others are, they may have, been used to living with a wood stove, and so they're comfortable if certain parts of their house are at different temperatures than others. So understanding this is going to really help you to design a system that's going to meet their requirements. Noise and aesthetic considerations are really important. It's good to know early on whether a person's very sensitive to noise and wants to have almost no mechanical noise in their life, and how much they're going to be affected by the visual impact of the outdoor unit on one of the facades of their house or next to their patio, as well as the impact of the indoor heads. And some people don't mind them at all. Others are dead set against having a ductless head in one of their rooms. And so then we have to figure out how all these different requirements mesh up with their budget. And we want to make sure that as we're talking about this, we're taking advantage of all the rebates and incentives that are available through New York State, and where appropriate, offering financing so that they can spread the upfront cost out over an extended period. Next, we need to figure out how much heating and cooling the building is going to need. And this is known as calculating the heating and cooling loads. This really has to be done thoughtfully. If the system is too small, it's not going to do the job, and you're going to have comfort problems in extreme weather. But too big is also a problem. A system that is too big is not only going to be more expensive up front, but it's going to be inefficient because it's going to be cycling on and off more often than it needs to. One of the analogies that people use is, you don't want to use a Mack truck to pull a baby carriage. And by a similar token, you want to make sure that the equipment that you're installing is sized correctly to the house. There's a procedure, a very well-defined procedure for getting that sizing right. It's provided by the Air Conditioning Contractors of America, and it's known as the Manual J sizing calculations. It's a set of spreadsheets. A lot of these are automated in various software programs, or you can do it manually with pencil and paper or a spreadsheet. But it's a very clearly defined process for figuring out how much heating and cooling you need for a particular building. Now, like any type of calculation like this, it's garbage in, garbage out. So in order to get accurate results, you need to have good inputs. And a couple of the inputs that matter the most in this calculation are air leakage. Air leakage is probably the single biggest thing that drives up heating loads in most of our buildings. And shading is really important in summertime because windows are where most of the heat gains are coming from in the summertime. So the more accurately you can measure air leakage, the more accurately you can describe the shading of the different windows, the more accurate your end results are going to be. It's also really important to remember that the Manual J process builds in adequate safety margins. So the last thing you want to do is do a calculation and then say, okay, well, I don't feel comfortable with the equipment that this is telling me I need. So I'm going to add my own informal padding to that, because this process already includes adequate padding. If you then add another 20 or 30% outside of that, you're going to end up with a system that's really oversized. As we're looking to electrify buildings, we need to make sure that the electrical service is adequate. And again, there's a really well-defined process to do to figure this out. You want to use the National Electrical Code, section 220.83. This takes you through a process that includes variables like the square footage of the house, the wattage of different existing appliances, the electrical requirements of the equipment you're proposing to install, and so on. And so it's again, a spreadsheet that will allow you to really get this right. You don't want to look at an electrical panel and say, oh, there's some empty slots in there. We've got room for a heat pump. Sometimes you can get away with that, but as you start to look at whole house solutions, and especially ones that include backup electric resistance heat, you really need to do these calculations carefully. And yet another thing you need to look at is if you're going to retrofit a heat pump into existing ductwork, you need to make sure that that ductwork is capable of carrying the airflows that heat pumps require. Because heat pumps are relatively low temperature heat sources, they require more airflow to deliver a given level of BTUs. So compared to a fossil fuel furnace, a heat pump is typically going to require about twice as much airflow. So we need to evaluate that existing ductwork, actually measure up the size of the different duct runs, and make sure that if we're going to be using a ducted heat pump here, we have enough ductwork to meet those flows. Oftentimes we find that we're enlarging the ductwork in one way or another, either adding in a couple additional supply runs or enlarging the return ductwork, or both. We also want to be aware of the location of the existing ductwork. If it goes through an unconditioned space like an uninsulated basement or a crawl space or an uninsulated attic, there's going to be additional heat loss that occurs in those spaces. And we need to try to minimize that for efficiency purposes, but we also need to build that into our equipment sizing calculations. We also need to make sure that any ductwork that's in an unconditioned space is adequately insulated. So once we know how much equipment we're going to need, we now have to start thinking about how we're going to distribute that and what the zoning options are for around the house. It's very tempting with these heat pumps to consider solutions like the one you see pictured here on the right, where you just go and put a ductless head, a high wall unit in every single room. That can actually lead to problems. And so it's something that we've tried to avoid. If you have a ductless head in a small room and it's the only head that's calling for heat, its requirements are going to be less than the minimum output of the outdoor unit. And so that outdoor unit is either going to be cycling on and off, which is going to make it run inefficiently. It's going to put extra wear and tear on it. Or that outdoor unit is going to be bypassing some refrigerant to other locations in the system, other ductless heads. And so you're going to get heating or cooling where you are not calling for it. And that also can lead to comfort problems. So when we have a house that has a lot of small spaces, ones whose heating requirements are below the minimum level of the equipment, the minimum modulation level, we want to be thinking about other solutions that we can bring into play. And these include compact ducted heads, which I'll talk about more in the next slide, as well as fully ducted systems like the one on the lower left here that can actually replace an existing furnace and use that existing ductwork to distribute the conditioned air around the house. I really like these compact ducted heads for small rooms, for a suite of small rooms like you might have in a typical 3-bedroom ranch where you've got, an open floor plan area, living room, kitchen, dining room. That's well served by a ductless head. But then you've got on the other end of the house 3 bedrooms and a bathroom. And those rooms generally have loads that are too small to require their own ductless heads. And so a compact ducted system like the one you see here is often a really great solution for that. It's a much better match. You can have ducts that run to each of those rooms, return in the hallway. And so it's a much better match for the heating requirement of those rooms. Plus, you now no longer have to get units on the walls of each of those rooms. When you have a very small room, like a bathroom, sometimes electric baseboard or radiant matting or radiant towel rack is actually a really great solution. So next, we want to select our system model and capacity. We don't want to just kind of take the nameplate tonnage. We want to actually look at how these systems are going to perform at the design temperatures we have in our specific location. To qualify for the New York State Clean Heat rebates, a whole house system needs to meet somewhere between 90 and 120% of the design load, I should say load, at design temperatures. Other things you want to take into account are the modulation range. All other things being equal, a system that can turn down further is going to provide more flexibility and more comfort. Is there going to be backup heating in the system? That may allow you to cut your sizing a little bit closer if you know that under very, very cold conditions, you have some kind of backup, either electric resistance or, you know, if the customers are interested in you know, firing up their wood stove in the very cold weather. That can allow you sometimes to cut your sizing a little bit closer and also make the system less expensive. One question that will come up sometimes is, are you better off with a single unit connected to multiple heads or to multiple outdoor units? And there's pros and cons to each of those choices. A lot of people prefer to have just one big thing on the outside of their house. On the other hand, having multiple outdoor units sometimes allows you to greatly reduce the length of the line sets that connect the indoor and the outdoor units. Smaller single head units oftentimes have higher overall efficiency and a greater modulation range. And I think there's also something to be said for having two completely separate systems so that if one of them goes down, you'll still have some heating or cooling in the house. And then there's lots of options for controlling these systems, ranging from simple handheld remote controls to sophisticated thermostats and you know, fully integrated systems that can be controlled remotely through your phone or tablet. This is just an example of extended performance data, some of the kind of thing you want to look at as you're selecting your system. Let's just look at this line of maximum capacity. For a heat pump, its maximum capacity depends on outdoor temperature. So this particular one, which is a Mitsubishi 1.5 ton heat pump, 18,000 nominal BTUs. When it's 47 degrees out, it actually can produce 30,000 BTUs. I can modulate all the way down to 5,000, so you've got, you know, quite a bit of range there. As you drop to 17 degrees, you've still got over 20,000 BTUs. At 5 degrees, it's holding steady. So you're still getting more than your nameplate rating all the way down to 5 degrees Fahrenheit. As you start to get into the negative temperatures, your performance falls off. But still you're getting significant amounts of heat output, even at minus 13, which, you know, for central New York, we very rarely see those kind of temperatures. These aren't wind chill temperatures, they're actual dry bulb temperatures that you'd measure with a thermometer. So this can help you make sure that you're picking a system that's gonna give you the performance you need when you are at those extreme temperature conditions. As we're thinking about where to put our indoor and outdoor units, with outdoor units, we need to think about visual impact, obviously, and we want to engage with the homeowners about that. We want to make sure that they're not too far from the indoor units, but also not too close. A lot of systems will have minimum distance between the indoor and outdoor unit, and that helps to reduce the amount of noise that you get inside the house. When possible, you want to avoid putting these too close to walkways or under the eaves or drip lines of the house. And you want to think about mounting options, whether you want to go with a ground mounted option like you see here, or a wall mounted option, which we'll talk about in one of the slides that's coming up. For indoor units, we want to work with the homeowners to decide where the visual impact is going to be acceptable. We want to make sure that we're observing proper clearance to existing furniture, windows, walls, and doors. That we're siting these units where their throw, meaning their projection of their airflow out into the space, is going to give good coverage. And we also want to place them in a way that makes it as easy as possible to dispose of the condensate, which is the moisture that gets pulled out of the air when they're air conditioning. More complicated and larger systems will also have devices called branch boxes. Those need to be located in some kind of sheltered space, whether it's a crawl space or an attic or a basement. Because they do have some relays in them that can make some clicking noise, you want to avoid putting those in the living space if possible. And then once you've come up with your design, or ideally a couple different alternative designs, you need to confirm your specification data, which means making sure that all the different equipment that you've chosen is going to work well together, that the sizes of the indoor units are matched to the size of the outdoor unit, that the total lengths of the line sets are within the limitations of the equipment. You can do this by just pulling up the engineering manuals. A lot of manufacturers like Mitsubishi and others now have software programs that allow you to drag and drop your different components, and it will flag with an error if your combination is not one that's going to work. This can also calculate what we call the D rates, which means that the system as designed may have different BTU outputs than what it says on the submittal sheet, depending on how long your line sets are, what specific combination of indoor and outdoor units you have, and your outdoor design temperature. So using a tool like this is Mitsubishi Diamond Systems Builder, can give you a much more dialed in sense of what your system's going to do as you've designed it. So just to quickly summarize some of the key points of applications, you do want to have in-depth, careful conversations with end users to make sure that you're giving them what they want. You do want to take the time to properly size the equipment. You don't want to assume that the existing ductwork or electrical service are adequate. You really need to gather the data and do the math to make sure it's going to work. When possible, you want to avoid putting ductless heads in small rooms. You do want to consider multiple options. Oftentimes I find that, these aren't as simple as a lot of, traditional swapping out a furnace or a boiler for another one. It really pays to consider a couple different options and then settle on the one, okay, this is really the most efficient, the most elegant solution. And then you always want to make sure that you're confirming your specification data once you've completed the design. The general process for installation starts by confirming the locations of the indoor and outdoor equipment. Generally, the workflow starts by installing the indoor units and then the outdoor unit. Once those are set, you can start to interconnect the refrigerant piping, the electrical, the condensate. Before you get any further, you really need to do a good leak test to make sure that your refrigerant piping isn't going to leak. And then evacuate the system to remove any traces of moisture or other contaminants that might be in it. At that point, you're ready to charge the system, which means releasing the refrigerant, power it up and test it. And then the key step that so often gets shortchanged is to educate the end user so that they're using these systems in the most efficient and durable way possible. We talked a little bit about some of the considerations that go into choosing a location. One of the things that has come up in research is that, the manufacturer will tell you what the minimum distance is to the ceiling. In this case, in this equipment, it's 3 3/8 inches. But that doesn't mean that's the most efficient distance. The closer you put the system, and here I'm talking about high wall ductless heads, the closer you put those to the ceiling, the more they're going to be drawing in that warmest layer of air that stratifies up along the ceiling. And because they're sucking in very warm air, that really both hurts their efficiency in heating mode and gives them a kind of an incorrect sense of what the actual temperature is in the room. So as much as possible, we want to try and get these units at least 6 inches down from a ceiling. With outdoor units, again, we want to make sure that the visual impact is acceptable to the homeowners. A lot of homeowners oftentimes don't have a good sense of how large and how big a visual impact these systems actually are until they see them for real. And so it's always good before you start tying everything in to walk around with the homeowner and say, okay, is this going to be okay where it is? Is that going to impact your view from your deck or your picture window or whatever? You also want to make sure that you've got adequate clearance, both for airflow through the unit, which is necessary for efficiency. You need to have clearance to shrubs, fences, other kinds of obstacles. But you also want to put it in a place where the future service person is going to be able to work on it without cursing your name. And one of the things that we found is whenever possible, you really want to avoid putting these under decks for just that reason, unless there's full standing height underneath the deck. Installing the indoor unit starts by locating the studs and securing the mounting bracket that you see here, drilling the hole that goes to the outside. This is a pretty typical installation on an exterior wall. Making sure that that hole is pitched properly down towards the outside so that the condensate can drain away from the unit. We want to install a wall sleeve, which is a device that helps seal that penetration so that you don't get outdoor air and insects and other things coming in. Attach the control wiring. That's easiest to do before the system's actually hanging on the wall. Hang the unit and then seal up the wall penetration. This is an example of a wall sleeve. It is just a telescoping plastic tube that lines the opening in the wall. It's very hard to get a good seal when you just take expanding foam like Great Stuff and just try and squirt it into a wall that might be empty. It might have fiberglass insulation in it or cellulose. If you use this wall sleeve, you give that foam something to contain it and you can get a much better seal. So we've gone to installing these wall sleeves on every time we have a hole going through a wood frame wall like this. Installing the outdoor units, it's important that they be level on solid ground, that you take the time to clear away mulch and get down to a firmly packed ground surface. We like to set the pad on a thick bed of coarse gravel. The unit itself needs to be up on a stand to keep it above the average maximum snow depth for airflow. In most of New York, you're okay with a 12-inch stand. We have, just as a matter of practice, gone to using the 18-inch stands in most applications. You also want to make sure that underneath the unit, there's free drainage, because in heating mode, this will collect some frost and moisture from the outside, and it needs to go into a defrost mode periodically, and you need to make sure that that meltwater can drain away freely. Otherwise, ice builds up and it can interfere with the operation of the system. Whenever possible, you want to install these in locations where they're not going to get a lot of roof runoff, such as right under the drip line of an eave or in a roof valley. If you if that's your only option, you might want to consider an awning or a we call a snow shield, a little sloped roof that fits over the unit and keeps the snow off of it, and also reduces the amount of water that drips on it in near freezing conditions, because that can also contribute to ice buildup. One of the things we learned the hard way is that you just really don't want to use these wall brackets on wood frame walls. Because these are variable speed heat pumps, the compressor and the fans operate across a wide range of frequencies. And more often than not, they will modulate through a frequency that causes that siding and that framing to vibrate in a way that creates a lot of very unpleasant noise for the occupants. So these wall brackets, if you're going to use them, make sure that you're using them on masonry walls. If your only choice is a wood frame wall, then you're much better off with a ground mounted mounting option. Once you've placed the indoor units and the outdoor unit, it's time to start interconnecting the system. And that involves the Linesets, which are the tubing that carries the refrigerant from the indoor to the outdoor unit and back. And mostly those are attached using a process of flaring, which we'll go into shortly. We need to think about Lineset covers, which is this white kind of downspout looking thing that you see here that not only protect the Linesets, but also give a much cleaner and more finished appearance. And we also need to make sure that the Linesets are properly insulated. Electrically, we have two sets of wiring to do. One is what we call the line voltage, which is the power that comes from the electrical panel through the disconnect, which is this gray box you see here on the right, and then into the unit itself. And then that powers the outdoor unit. The outdoor unit is actually what sends power to the indoor units. And so there's, we call control wiring. It carries signals back and forth between the systems. It also powers the fans in the indoor units. And then we need to make sure that we're doing the condensate piping carefully so that we don't end up with moisture running down a wall or dripping from someone's ceiling. To make a good flare, which is the type of connection that we are typically using on these systems, you need to get all these steps right. You need to cut the copper correctly, deburr the cut, forge the flare to the exact dimensions necessary, assemble it, tighten it to the correct torque, and then you really need to test it. And we'll go through a testing protocol that can eliminate the vast majority of refrigerant leaks. A good flare starts with a good quality tubing cutter with a nice sharp cutting wheel. You want to make sure that you're taking the time to make a nice square cut and that you make that cut gradually so that you don't pinch or deform the tubing. The next step is to deburr the tubing, which means removing that little thin lip of copper that forms as the cutting wheel presses into the tube. And you want to do that carefully so that you don't gouge the piping, so that you don't get any of the little copper shavings in the system, and that you don't get overzealous and thin out the tubing wall to the point at which you've weakened it. The next step is to create the flare itself, which is a little cone that you make by with one of these tools. The end of the copper is actually flared out and it fits over a brass cone, which we'll see in the next slide. There are a number of different flaring tools. I have mostly used the one on the left, which is known as a eccentric cone flaring tool. You can see that it's got different holes for gripping different sizes of copper tubing. It's got a depth gauge so that you can insert that tubing just to the right depth to get the correct flare dimension. And then you turn this, this handle and it spins a cone inside the copper tubing and pushes it out into a correct flare. It has a clutch so that when you're done and you've got it to the correct dimension, it doesn't keep going and crush and damage the flare. Other commonly used flaring tools are this ratcheting flaring tool, and one that's becoming increasingly popular is one of these cordless spin flaring tools. The people that I know who have used these absolutely love them and say that even a relatively inexperienced person can make perfect flares every single time. Once you've made the flare, you want to make sure you take the time to inspect it. This is a really critical step to make sure that it's symmetrical, that it's shiny, that that inside surface is really perfect, because that's what forms the mechanical seal that holds in the refrigerant. In this picture on the right, you can see a flared tubing fitting over a cone, and you can see that these two parts need to match up perfectly in order to form a tight seal. And then the flare nut is tightened down over that to the correct torque, and that compresses that fitting and keeps the refrigerant in. I really like using what's called an assembly lubricant when you're putting together these flares. The one that I've used a lot is called Nylog. Essentially, it is a product that's made out of refrigerant oils, but it's thicker. And what it does is it assists in assembling and tightening this flare. It lubricates the back of the flare nut so that it doesn't bind as you're tightening it down. And it also helps to form a good molecular seal between the brass cone and the copper flare. So whether you're using a product like Nylog or just pure refrigeration oil, either one of those is going to help make a good flare. You want to be careful not to over apply this stuff, because not only will it get into the system, but if you use too much of it, it can affect the torque specs and allow you to over torque and over tighten the flare nuts. So use with restraint. One of the key things that a lot of both beginners and old school techs will not do, that really needs to be done, is to use torque wrenches when you're tightening down the flare nuts. We work with a range of different tubing sizes, and each of those requires a different torque setting. If you tighten a flare down too tightly, you'll crush the flare and you'll oftentimes have a catastrophic leak. If you don't tighten it enough, you can also have a leak. And a torque wrench is a device that allows you to get that just the correct amount of tightness. You can see that there's different settings that vary with the diameter of the tubing. A person that just says that they can do it by feel is going to have a tendency to over tighten the small diameter tubing, the small flares, the ones that only require 13 or 15 foot-pounds, and to under tighten the big flares, the ones that might require 50 or more pounds of torque, foot-pounds. A couple other tips that I've learned along the way. One is that if you test a flare and you find that it's leaking, don't put wrenches back on it and try to tighten it some more. That's not going to work. You'll end up over tightening and ultimately crushing the flare. You don't want to use other leak sealants like Leak Lock is a brand that is used for other applications. It's not to be used on flares. You don't want to use, some manufacturers will sell pre-flared line sets. Both my own experience and almost everyone else I've talked to about this says they're junk. Best to cut them off, make your own flare using your own tool. That way you know that you don't have something that was done improperly in the factory or damaged in transit. Whenever possible, you want to use the original equipment manufacturer's flare nuts, the ones that are provided with the equipment. Those are matched to the torque specs that they give you. If you use an aftermarket flare nut, not only is it going to be, for the most part, poor quality in terms of its metallurgy and so on, but it will not necessarily have the same torque specs as the manufacturer's planets. And then one more point to mention is that sometimes you will see the line sets coming out of an indoor head have tubing of one size and flare connections of one size, and those are connecting to a port on the outdoor unit that is of a different size. You always want to consult the manufacturer's guidelines on this, but generally it's going to be the indoor head rather than the port on the outdoor unit that determines the correct line set size. And then not to be neglected is the importance of line set insulation. Not only is that insulation there to prevent unwanted heat loss and heat gain, but it's also really critical in preventing condensation for the parts of the line sets that go through the walls and into the indoor unit. So you want to make sure that you do a thorough job of installing and securing that line set insulation. The electrical system, essentially, this just needs to be done per manufacturer's instructions and code. The submittal data on a particular piece of equipment will tell you what is the correct wire size, the correct ampacity of the circuit, and the correct breaker size to use. You need to have an outdoor disconnect, which is basically allows you to cut off power to the unit so that a technician can safely work on it and not worry about someone inside the house flipping a breaker and suddenly energizing the unit. The outdoor wiring needs to be properly protected by conduit. And we're increasingly encouraging homeowners, and we've just made it a standard practice in our company to install surge protection on that outdoor disconnect. That way you have some protection from lightning strikes and other surges that can occur, and it can prevent you from having damage to the electronics inside the system. As far as the control wires go, it's really important to follow the manufacturer's recommended wire gauge. With line voltage wiring, it's often okay, if more expensive, to use a heavier gauge wire. With control wires, you only want to use exactly what the manufacturer tells you to do. And that's because these control wires not only carry power to the indoor unit as an alternating current signal, but they also, overlaid on top of that alternating current, they are conducting a small direct current control signal. And in order for this to all work as designed, you have to use exactly the manufacturer's gauge, that the wire gauge that the manufacturer recommends. It needs to be outdoor rated. A lot of supply houses are now carrying mini split control wire designed exactly for this application. And because of this issue with the direct current control signal, if possible, you want to avoid splicing that wire and just have a continuous cable that runs all the way from your outdoor unit to either your branch box or your indoor units. Condensate is really important. It's easy to do, but if you don't take the time to do it correctly, you're going to end up with problems. Most of the time, we're relying on gravity to drain the condensate away from these systems. And when you do that, you just need to make sure that that piping slopes consistently away from the indoor unit at least 1/4 inch per foot. And that when it exits and drips out, it's not in a puddle or a pile of mulch or dirt or something like that where it's going to be clogged, because that water can back up. Most of these ductless heads don't have any kind of safety switch to shut them off when that condensate line gets blocked. Those can be installed, and in fact, probably should be, especially in really critical applications. But what you will end up with is, if this condensate drain gets clogged, you will end up with water running down the interior wall. Condensate pumps can be used in applications where gravity draining for one reason or another isn't possible. For example, if you're installing one of these in a basement and you need to go up before you can drain it away, you can install one of these aftermarket condensate pumps. These tie directly into the power on the indoor head, and these can incorporate a safety switch so that they will shut off the indoor head should for any reason this pump fail or become blocked. One of the drawbacks of these condensate pumps is that they are not silent, and in some cases can cause an annoying noise level, especially where homeowners have an expectation of extremely quiet system. So once you've got the system all interconnected, it's really critical to check the system for leaks. Refrigerant leaks the system can't work if it doesn't have refrigerant in it. And if it's losing refrigerant, its performance is going to fall off over time. It will also live a short and inefficient life. When systems are low on charge, the compressors will fail prematurely. But the other reason to be concerned about refrigerant leaks is that refrigerants themselves are very potent greenhouse gases. So everything we can do to keep them in the system and out of the atmosphere is for the good. The majority of leaks can be prevented by thorough testing. And what we've really settled on is a kind of a 4-step set of tests to catch leaks before the refrigerant goes in. And this takes time up front. If you do all these things, it may add 45 minutes or an hour to your installation, but it's going to prevent callbacks and all the other problems down the line. The 4 steps that you need to do are: first, fill the system with high pressure nitrogen. It needs to be able to hold that pressure. You don't need to do a 24-hour test, but you need to make sure that your gauges are holding steady for 45 minutes or an hour. While you're doing that, you want to spray all your flares with a bubble solution, a leak check solution. And if you see bubbles forming in any of these flares, you know you have a leak and you need to redo that flare. If we pass the standing pressure test and the bubble solution tests, it's time to vacuum down the system. And there's an additional test you can do at that point called the vacuum decay test. So you want to vacuum your system down into a deep vacuum to remove all the moisture and all the air and other contaminants that might be in the system. And then you turn off your vacuum pump, you valve off the system, and you watch, okay, is this system holding its vacuum? And that provides, it's not suitable as a primary leak check, but it will catch some leaks that the standing pressure test won't. And then the last step is, after you've released refrigerant into the system, go through and check all your flares and your service valves and so on with an electronic leak detector. And that way, if you do have a small leak at any of these locations, you will have caught it while you're still on site and you can repair it rather than getting that call back later that the system's not working. Most systems come pre-charged to a certain length of line set. When you have longer line sets, you will need to add additional refrigerant charge. So you need to measure out the lengths of your line sets and weigh in the proper amount of refrigerant. It's really important to record the amount of refrigerant you've added too, so that if a future technician comes through and needs to pull the refrigerant out of the system, for example, they'll know what you put in there, they'll measure what they pulled out, and that may indicate that there's a leak. It may also, it'll give them the information they need to put the correct amount back into the system. Make sure the controls are configured properly, that the different parts of the system are communicating with each other. And then put the system through a test run where you not only make sure that it's starting up, no error lights are blinking, that you also want to check to make sure that whether you're running it in heating or cooling mode, that you're getting the correct amount of temperature change across the indoor units. So, and that's one way to verify that the system is working properly. If you have a ducted system, you also want to check your airflow. and measure your static pressure. And there's a more sophisticated test that you can do where you actually can measure the BTU output of the system based on the airflow and the temperature change across the indoor units. I'm going to attach an article along with the slides for this that explains how to do that. It's not something you necessarily need to do in every single installation, but it's a good tool to have in your tool bag in terms of troubleshooting and diagnosis. And then also critical is end user education. One of the things I've found is that, most of our best techs are not necessarily great educators. And so what we've tried to do is build more education into the entire process, from sales and design through installation and service. Explain to people how these systems are supposed to operate. They are going to be different than the fossil fuel systems that you're used to. So we need to create realistic expectations. Most heat pumps are not going to perform well if you turn the temperature down to 50 degrees when you go off to work and expect to crank it back up to 70 when you come home. Generally, a set it and forget it strategy works a lot better with these systems. You want to talk people through the basic operation. Most of these systems come with very complicated controls, and really there's only a handful of buttons that you need to use to operate the system properly. But customers will oftentimes ask, oh, how do you do this? How do you do that? What we try to do is give them a basic orientation in the system, explain how we recommend using it, and then say, if you want to dig deeper, here's the manual. You want to go over the warranties on the system. We like to register equipment for the homeowners. That way we know that it's been properly registered with the manufacturer. And you also want to talk to them about maintenance and service, both the DIY maintenance that they can do themselves, mainly keeping the filter clean and changing the batteries on their remote controls, and then the annual service that you need to keep the system clean and properly checked and running at maximum efficiency. One of the things that we found really helpful in this education process is a quick guide or cheat sheet that we can give out at the finish of an installation. You can see a copy of it here, and this will be in the slide deck. HeatSmart Tompkins also made a more generalized version of this that I think is really useful to help, especially less technical users, just remember, okay, these are the basics. This is what I need to do to get the system to heat or cool, and here are the few things to try before I call my contractor and tell them that it's not working. We also like to use this as an opportunity to reinforce the importance of regular, both self-maintenance and professional service. So, quick run through of the highlights of applications. We don't want to mount the outdoor unit. That should say indoor unit. Don't want to mount the indoor unit too close to the ceiling. We do want to seal the wall penetrations well to avoid air leakage and potentially moisture and insects coming in. We don't want to use wall brackets on wood frame walls where they can create noise problems. We do want to elevate the outdoor unit above snow depth and for free drainage. We do want to carefully follow the manufacturer's instructions for wiring both the line voltage and the control wiring. We don't want to skimp on leak testing. We want to go through all 4 steps of a proper leak test to make sure that, to the extent possible, our system is free of leaks. We do want to put the proper amount of extra refrigerant trim charge in the system and record it. And we do want to do a good job of educating end users in the proper operation maintenance of the equipment. As we get more and more of these systems out there, operation and maintenance are going to become a bigger and bigger part of what we do with these systems. We want to try and get people on a schedule of annual preventive maintenance. The technician will do a visual inspection. They'll clean the filters and the coils. Depending on how much air conditioning they're doing, they may need that blower wheel cleaned every year. It may be an every other year kind of thing, but at least it should be looked at. It's really critical to clean and check that condensate pan and piping. That's where mildew and funky odors can occur, and where clogs can occur that are going to lead to leaks. Put the system through its paces with an operational test. Here's an opportunity to do more of that delivered capacity testing that I was talking about, ways to test the system without hooking up the refrigerant gauges. And that's really important because each time you hook up gauges, you can lose a little bit of refrigerant, and over time that's going to degrade the performance of the system. And then if there are any problems, we want to make sure that our technicians are trained to diagnose problems with airflow, with refrigerant charge, with electrical problems, control, configuration, and so forth. And sometimes we just have to talk to the homeowners about the way they're operating the system. And oftentimes there are problems can be solved by just understanding what people are actually trying to do with their systems. Non-invasive testing involves using probes like these Testo Bluetooth probes that I'm using here. I'm testing a floor-mounted Mitsubishi unit here, and I'm measuring the humidity of the supply and return air, the temperature of the supply and return air. And I've already measured the airflow using a little anemometer. And I have an app on my phone that takes these data and converts it into BTUs being delivered. And this is a way to, verify that the system is giving the correct BTU output. If it's still not doing what you want, you can at least know that the refrigerant side of the system is working properly, and you can move on to things like controls and operator behavior. Increasingly, we're seeing heat pumps come with more sophisticated diagnostic tools. This is a little device that you can hook up to LG heat pumps by a little quick connect plug, and it will read out to your phone all kinds of data, basically give you access to all the internal sensors in this system, which is tremendous in terms of your ability to troubleshoot these systems. And I really think these are the future. This is going to allow a technician with fairly basic training to hook up one of these things, be in communication with a super tech or tech support person back at the home office who may be supporting multiple techs out in the field, and just give us a lot more insight into what's actually going on inside these systems. So highlights of operation and maintenance. We do want to make sure these things are getting maintained regularly, that they're being kept clean, especially the heat exchangers, the blower fans, and the critical condensate pans and drains. We want to avoid hooking up gauges to these systems. The only times really you should be hooking up gauges for the most part are when you're doing the initial pressure testing and when you're recovering refrigerant from the system. And you do want to get more comfortable using non-invasive diagnostic tools. Some additional resources that are worth knowing and checking out. Of course, the NEEP guidelines that I mentioned earlier, those are really fantastic. And a lot of the recommendations in this talk are based on the NEEP guidelines. Green Building Advisor is a website that contains excellent content. There's a lot of discussion there on best practices around, especially design of cold climate heat pumps. There's a white paper that was produced by Building America on the field performance of inverter-driven heat pumps in cold climates, where they actually hooked up some pretty sophisticated monitoring equipment to a bunch of these systems installed in New England. and got some insights. This is the study that led to the realization that it was really important to get as much clearance from the ceiling as possible. And that's a really interesting paper, both for the techniques they used and for their conclusions. There's a wealth of manufacturer literature that's available online. I know all Mitsubishi and LG technical data is not behind any kind of login or large parts of it. Great amounts of resources are available without a contractor login. And then a couple articles that I'll be sending along. One is Cold Climate Heat Pumps Do's and Don'ts. It kind of goes over a lot of the points that I talked about here in more detail. And the article on performance testing ductless systems talks about non-invasive tests that you can use to measure delivered capacity. Here's my email down here. If you have any questions or just want to talk further about any of the things mentioned here, please don't hesitate to drop me a line. And the last thing in this series is a hands-on workshop that's going to be offered on Saturday, November 7th in Ithaca, New York. We are going to be installing a cold climate heat pump start to finish at a Habitat for Humanity house here in Ithaca. Conrad's going to talk a little bit more about the sign up for that, but we are limiting attendance just so that people can get some hands-on and so that we can maintain good social distancing and COVID safe protocols. But I do believe we still have a few slots open. So if this is something you're interested in, please sign up as soon as possible. And with that, I'm all done and ready to take some questions.
Very good. We do have some questions, John. Thank you very much. And I will just address the last thing you spoke about, the hands-on workshop that we're doing on November 7th. Yeah, I think there are 2 seats still available. But as we always say, if the demand exceeds our supply, we'll make more supply. We can do additional sessions as long as we have good demand. So we have a couple questions.
Conrad, Conrad?
Oh, sure.
I was going to talk about the hands-on training.
I'm sorry, I was going to put you at the end, Brian, but
yeah, well, I thought I'd get here before people might leave the conversation. I'm Brian Eden. I'm the chair of HeatSmart Tompkins. I'll be administering the event, the hands-on training. So I'll be in contact with people that have signed up, and we are hoping to, have that information out to you by next week. If you've already signed up, if you haven't signed up, please do. We do have more than enough to attend, but we would, some people are not going to be able to do that because of circumstances. So I'm asking people to be very clear about their commitment, because I don't want to find out the night before that you can't come, and we have the limited number of spaces, so we want to utilize those to the full extent and get everybody that we're hoping to have to meet our capacity. And so we, Ithaca is in a relatively low infection rate. We've committed to doing this. I mean, I could understand where some people might feel that they might not want to do that, but we will be observing COVID safe practices throughout. We'll spend a good majority of the time outside. And so we'll be sending you some reading materials at the beginning of next week and more details about where the training will occur and more information on what will take place that day. So, I'm thankful for you attending this webinar, and we had a very successful hands-on training in August. Really, the folks are very engaged, and we're hoping to replicate that with this one, and we're hoping to have another. If there's enough interest, we'll have another hands-on training when maybe Q1, at the end of Q1, early Q2 next year, when the weather is a little bit better, and maybe we're free from some of the concerns that we have about COVID exposure now. So anyway, that's it. I'm looking forward to you coming, and we'll be here to serve you, and hopefully you will be able to do this. Thank you.
Very good. And one of the questions, Brian, before you leave, one of the questions is about the video. I believe there was someone doing video of the installation, the last one we did in August. Is that video available? Has it been edited? Is it usable?
No, actually, the videographer did not come, and so we have no video of that event.
Okay.
We'll try to, do better this time, but we'll be careful if people are interested in not being in any shots or things like that. We'll protect your privacy. I mean, you'll have a mask anyway, and we're gonna, you have to wear a mask. That, we're need to comply with NYSERDA's COVID safe practices, and so we need to do that. And so anyway, that more to talk about that when you come to the event.
Very good. And I'll just mention that the August event, we had no reports of any infection. Everybody did great COVID distancing, and worked out fine. So I don't think there's an issue there. You have to get in close, but we can still navigate that the distance for safety.
Continue to have communication with the people that attended that. They were all very satisfied, and we had a bunch of questions to follow up the training, and we'll hope to continue to support your questions after the training.
Very good. Sure. Okay, so John, we have a couple. Thank you, Brian. Thank you very much. And thanks for sponsoring this event. Thanks for all you do. John, we do have a couple technical questions. What level of deep vacuum do you pull to at different stages of your installation?
Right. So, kind of the traditional best practice for evacuating a system would be a triple evacuation, where you bring the system down to a certain level, say, 2,500 microns, put dry nitrogen in it, vacuum it down deeper, and then do this till you have your final finishing vacuum, which is going to be below 500 microns. As we've gotten better micron gauges and greater understanding of the process, we've moved away from triple evacuation towards a single deep evacuation. So typically we're evacuating down below 200 microns, oftentimes closer to 100 microns. And then using the vacuum decay test to rapidly tell us, have we kept it in vacuum long enough? If we pull it down below 200 microns, our decay test target is 500 microns. It needs to stay below 500 microns for 10 minutes. And there are different standards. That's the one that we've kind of come to. But there are really sophisticated gauges now that can speed that process up a lot. So they can measure the rate at which the vacuum is decaying and tell you, okay, within 30 seconds, it will tell you, okay, you're going to pass this test at 10 minutes. We've also looked at other improvements to the vacuum process. For example, being sure that you remove the Schrader cores in the system, and that you use the largest practical diameter vacuum hose can radically speed up the vacuum process and still give you very good results.
Very good. What about surge protection? You mentioned that was important. Can you suggest possible circuit breaker surge protection specific to a panel, or is there a strategy, any one strategy that's better than others?
Yeah, so most of what we use are HVAC specific surge protectors. So, it's coming down the line that whole house surge protection is going to eventually be required by code in new homes and service upgrades. But for a small fraction of that cost, we can install a surge protector on the outdoor disconnect. And essentially what this does is anytime there's a surge voltage, in this case, it's above 300 volts, this device will shunt it to ground. And so it'll prevent it from getting into the system and damaging the electronics. These surge protectors have a limited lifespan. They typically have an indicator LED that will tell you, okay, this one has absorbed enough surges that it's no longer effective, and that LED will go out and you'll have to replace it. And they're not terribly expensive. They're typically $50 to $100 part that can potentially save you all kinds of downtime and expensive circuit board replacements. So I feel that they're really a good thing to have. I'm kind of surprised that manufacturers don't just build them into the equipment, but you can put them very easily right on the outdoor disconnect.
Very good. You spoke about non-invasive diagnostic tools, and the example you had was a great example. This seems like a really good way for contractors to offer proactive services. I remember seeing a presentation at the recent Home Performance Coalition conference where a contractor was using these tools to learn about problems with the HVAC system even before the customer noticed them. And that just seemed like a very proactive way to do it. Can the tool that you highlighted there and these tools in general, can they be set by the contractor, or can they have alarms that a contractor could access, or are these customer-based tools?
Yeah, so for ductless systems at this point, we're mainly looking at tools that the contractor carries around in their van and uses to measure things. We don't have a good system for continuous monitoring. This is a place where, geothermal industry is really way ahead of us. They've been doing performance monitoring for years, where the installer can see what's going on in a geosystem through a Wi-Fi link from their home office. And we're seeing that increasingly in Carrier, and I believe Train now have systems like that. Right now with the cold climate heat pumps, I'm not aware of that kind of monitoring technology that would allow us to do, remote diagnosis without actually going to the site and either plugging in our monitoring device or doing that non-invasive testing.
Okay, very good. You mentioned mini splits have made overhead units almost the standard, but it seemed to me in your discussion that you were suggesting that the lower it is on the wall, the more efficient it might be. Are floor units more efficient? I mean, you're putting the outside unit at the same level as perhaps you could put the inside unit, which seems very intuitive there. But would that be more efficient than an upper unit that was up on the wall?
Yeah, we're predominantly a heating climate. And so in general, it works better to supply that conditioned air lower in the room. So those low wall units, like the one I showed in one of the slides, those are really ideal both for comfort and efficiency. They're not as widely available. And the other issue that we run into a lot is that people just don't want to give up that low wall real estate. The place that they have available to put these units is high up on the wall. And so that's a limitation. We are seeing.
And in cooling mode, I would imagine it works better to have it high up on the wall.
Yeah, they're ideally placed for cooling, for sure.
Mhm. Very good. So there's several tests. It seems like most HVAC installers probably would not do. Your blower door test to quantify air leakage seems like a critical part of the manual J. Your air handling system, testing for leakage in that air handling system. Are these tests required for rebates, for utility rebates? And if so, do they have to be done even with a mini split system? Or are they only required for a major centralized home system?
Right. So the utility rebates, which are the main rebates that most people are accessing around the state, do not require a blower door test. I really like having that data because I feel like it gives me a lot more confidence in my sizing calculation, but it's not required. Now, if you are participating in the NYSERDA low income programs, like Empower New York, Assisted Home Performance, the ones that are gonna, piggyback on the utility rebates and in some cases cover most or all of the cost of the heat pump systems, they are gonna be asking for blower door numbers.
Even the utilities are asking for blower door numbers?
No, not NYSERDA's Empower New York and Assisted Home
Okay,
Performance.
I'm sorry.
They're gonna, there are cases when you can't do a blower door, for example, if it would disturb asbestos. But in general, they are asking for blower door numbers in those lower income programs.
And are you still doing blower door tests in COVID season?
Yeah, so this just recently changed. I think there was some fear that by doing this blower door test and moving air around the house, you would increase the likelihood of COVID transmission. It never made sense to me because what we really want to do is dilute that indoor air, and blower door does that dramatically. NYSERDA has just recently, in the last month or so, come out with a COVID safe blower door protocol. And the main pieces of that are that you run the blower door with a window open for a couple minutes before closing things up. And that way you purge air through the house. And that you then also sanitize the blower door in between visits.
Very good. Yeah, happy to see that, that movement in that direction. One more question, data points. I think you debunked the idea that we had good remote monitoring, but if we were to have good remote monitoring, what kind of data points would be best? There are many thermistors that exist within a heat pump. Would remote monitoring of temperature at the internal thermistor level be of value to a service company, perhaps?
Yeah. I'm the kind of person that wants to see as much data as possible. Mini splits are packed with sensors, and so they're measuring temperature of the refrigerant at oftentimes 7 or more different points in the system. In the indoor coil, the indoor air, the outdoor discharge line, the outdoor suction line, and so on. And so with this data, you can get a really detailed picture of the state of the refrigerants in the system. And you can ask different questions with that. I think what we're gonna see is apps that kind of resemble what you see in commercial energy management, where you might have on your tablet a diagram of the refrigerant flow in the system, and you can see the temperatures of the different sensors. And you can combine that with data on electrical consumption and fan speeds, and that will give you heating, cooling output. It will also give you energy efficiency in real time. And so all that data exists. It's just not accessible to the contractor yet.
Right. Yeah, all in good time. And speaking of time, it is 6 o'clock. And you did a great job, John. Thank you so much for your time today. Thank you to all the participants that that are here. And hopefully you got something out of it that you can use. And if not, reach out and we'll make sure you do get something out of it that you can use. So thank you all for being here. Thank you very much, John. Thank you, Brian. Thank you, Elizabeth. Signing off for now.